by taking, yeah, I think it's just my laptop, by taking a locally optimal choice, which means at every step, right? If you're trying to solve a problem that involves like making a lot of choices, greedy just means at every choice, you take the best option right now without thinking like into the future, like how that's going to affect you. And hopefully in some problems that will lead you to the globally optimal uh, solution, which means, the best possible solution of all the solution sets. And it's often very simple to implement because just each step you have to just choose like the best option, which can often mean just like sorting a list so that you know like the highest numbers. Or I don't know if you guys know what a priority queue is, or a heap, which is just a data structure that can um, take a bunch of numbers or items and give you like the highest or lowest amongst them. So that's often involved to just select like the highest or lowest value. And they're also pretty fast. They'll quickly lead you to a solution. But again, they don't work for every problem. And we'll see that later. We'll talk about another category of algorithms that or problem solving techniques to solve problems that greedy doesn't work on. The one difficult thing is it's sometimes difficult to think of what policy, like what greedy policy will lead us to that optimal solution, because sometimes there's different ways to think about greedy, and you have to be a little bit clever when thinking like what to optimize. It's not always necessarily simple as just like take the highest number. And we'll see that when we talk about some example problems. So this is a pretty classic example. It's called interval scheduling. It's often phrased as, imagine we have a bunch of meetings that have like a start and end time, and some of them overlap. So for example, you can see A and B. B is completely contained within A. And so we're going to say that we can't have meetings that overlap going on at the same time. Like let's say we only have one room. So we can't have meetings that like two meetings going on at the same time in the same room. And so our goal is to try and from this like set of meetings, try and find how many meetings, just maximize the number of meetings that we can have going on without intersecting with each other, without overlapping. So for example, for this set of meetings like A, B, C, D through H, the optimal, or one of the optimal solutions is B, E, and H. So those can all go on, back to back, like B ends and then E starts and ends, and then we have a little gap actually, and then H starts and goes. Uh, and then as I was saying before, the difficult thing is actually the greedy policy to find the optimal solution in this case. Because if you were to, for example, the actual scenario, the actual solution ends up being choosing the meeting with the earliest endpoint, right? So we sort the meetings by earliest endpoint, which it doesn't look like they are here actually. But like, for example, B has the earliest endpoint. B ends the earliest of any of them. And so we take that first. And then we go to the meeting with the next earliest endpoint, which is A or C, they're both tied. And then we say, can we take it? Like we've already taken B. Could we also take A or C? And we can't. So we just keep moving on, going up endpoints. And then E is the next one. It has the next earliest endpoint. And if you were to optimize a different uh, like policy, like if you're trying to if you were to try and say take the meeting with the earliest start time, right? Like try and schedule a meeting that starts really early, that would actually lead to in some cases not an optimal solution. Or if you were to take the solution with the shortest time, if you thought like, oh, we want to schedule a lot of short meetings, that doesn't actually always lead to an optimal scenario. And I can draw out, I think, like for example, is there anywhere? What's a good place to draw? Like if we had, I'm trying to think of a counterexample. So for the shortest meeting, for example, let's say these like lines are meetings. This meeting is in the middle, is shorter than the other two meetings. But if we take it, then we cannot take any of the either of the other ones, right? Whereas we could take the two meetings that are longer and schedule two meetings. So that's kind of a counterexample to show that you shouldn't always take the shortest meeting. So sometimes realizing and sort of thinking to yourself about what to optimize in the greedy choice is sometimes pretty difficult. And we'll talk a little bit more about like how to do that. Uh, okay. No, I erased it. I can just undo. Okay. And the next problem we're going to be talking about is also a pretty classic problem. It's called fractional knapsack. So a knapsack is what some people call just like a bag. And the idea of the problem is we have a bag that can store some weight. We have some capacity for the bag, and we'll call that W. And we also have some items that all have their individual weights and their values. So here we can see a set of items A, B, and C that have their own weights: 2 pounds, 2 pounds, 3 pounds, and their values: $100, $10, $120. But the fractional part of this problem, fractional knapsack, means we could take just part of that item, right? We could take 1 pound if we want and get the fraction of that value. So for example, if we wanted, we could just take a pound of A and get $50. So we don't have to take the whole thing. And so we want to maximize, of course, the value in our bag. Basically, we're trying to fill the bag with as much value as possible. And in this case, this is actually a pretty simple greedy policy. We just want to take the highest unit value of an item, right? So for example, which means like the value per pound. So for example, which has the highest unit value here? So C is $40 per pound, like $120 divided by 3. A is $50 per pound because 100 divided by 2. So even though C is overall more valuable, it's better to take A. And the fact that it's fractional actually is really important to the problem. There's many other variations of the problem, and one, if you couldn't cut up the items like this, you could not complete it greedily, and we'll see that later. We'll talk about another variation of knapsack that you can't solve greedily. And we're gonna do an example problem, which I'll open up. So this is maximum number of coins you can get, which we code. Oh, you can't see it. It's 1561. How am I going to do the mic and type at the same time? I like the old way up. Okay, I guess I'll type with one hand. I could crouch. Okay, I'm going to do this in Python because you guys know Python from Programming 1, right? So everyone's comfortable with that. So first, let's just read the problem statement. So we have 3 n piles of coins of varying size, and we're going to take some of those piles according to these rules. So at every step, we choose 3 of those piles. So the piles are just numbers, really. And the piles don't have to be consecutive. We can choose any 3. And Alice, so not us, gets the highest coins highest number of coins in those piles, the largest of those piles. Then I'll pick the next largest, right? The next pile with the maximum. And then Bob will pick the third. And then repeat until we run out. And because they say 3n, it means it's a multiple of 3. So we'll be able to do this without having any like leftover, we'll never have 2 piles or like 1 pile alone at the end. So if we look at some of the examples, it's not necessarily given in any order. It's just these piles. So 2, 4, 1, 2, 7, 8 are our pile sizes. And this explanation for the solution. So this is saying that best we can get is 9. So we're trying to maximize, of course, the number of coins we get. We want all the coins. So this is saying one way to get 9, which is the optimal solution, is to choose 2, 7, 8. Alice gets 8, we get 7, and Bob gets 2. And then choose 1, 2, 4. Alice gets 4, we get 2, Bob gets 1. So if we write out, so let's just think about the problem before we start coding, right? Okay, this is gonna be harder than I thought. So the first thing to notice is that since Alice gets the maximum of all the coins, is that if any of our piles, so let me type out an example here. If we have 1, 2, 3, I'm just gonna write it in sorted order. It's not necessarily delivered this way, but just for us to visualize. If any of these piles, so 9 is the highest of all these numbers. If we ever select a trio of piles that includes 9, 9 will obviously be the maximum of those 3. So Alice will always get 9. We have no chance of getting like the maximum of our list, but we can get the second maximum of our list, right? So if we included 9 and 8 and then anything else, Alice will get 9, we'll get 8, and then Bob will get the third thing. So the first thing to realize is Alice is always going to get the maximum. And then when she gets the maximum, we should get the next maximum, right? Because for example, if she chose 9, if we chose 3, if we chose 3 piles that include, and one of them was 9, Alice is always going to get that. And so we should also choose 8 at the same time, because if we chose something else, like if we chose 9 and 7 and then something else, then Alice would get 8 on the next turn. So we know we want to choose like the first two, like the highest value, the highest 2 values. And then the only question left is, what should we leave Bob? So Alice gets the highest, we get the second highest. And then the best thing to do is not give Bob the next one, but we want to just give Bob the lowest amount possible to get rid of the small coins. So we want to give Bob the 1, right? So we'll give Alice, we'll choose not, so at first, and in general, we'll choose the highest 2, and then the smallest. And that will mean we always get the second of those 3, right? The middle one of those 3. And if you want a counterexample, for example, like to show that we shouldn't get Bob, we should give Bob the smallest one. If we were to, in this case, choose 9, 8, and 7, which this is going to end up being wrong, because we'll get 8, but then Bob will get 7, right? So we have 8 total. So we have 8. This is a running counter. But then, and then in the next case, when we choose, we're forced to choose 1, 2, and 3 are the only piles left. Alice gets 3, we get 2, and Bob gets 1. So we get 10 total. But if we had done what I said originally, which is the greedy correct solution, where Alice gets 9, we get 8, and we leave Bob with the smallest 1, then we start with 8, but on the next go around, we get 7, 3, and 2. So we get the 3 instead of the 2. So we'll get 11 total, right? Or sorry, 11. So that's our solution. Choose the highest 2, and then the smallest one goes to Bob. And actually, when we're coding this out, we just need to get the amount we're getting, which means we don't really care about like what Alice and Bob get in terms of like, we don't need to keep track of that. So we can just go, it's always going to go like this. We remove the highest 2 and we move the lowest 1, which means we'll always be getting like the second, we'll be going in 2. So we'll get, for example, here we'll get 8 and then we'll get 3. So we just skip over, we just like get every other one starting from like the second highest. So let's write that out. Yeah, go ahead. Oh, sure. Sorry. Is that good? Okay. Could you read my comments before? Okay, that's good. Sorry about that. So another thing is I forgot to mention again, or I did mention, but I didn't bring it up again. These piles are not sorted on initially, so we'll have to sort them. And that's a common thing you have to do. For example, that happened in the intervals. We had to sort them by the ending time. So we'll sort them. And so that allows us to easily see like what's the largest, and second largest. So the way I'm going to do this, and there's different ways you could write this, but I'm going to say, I'll call end like what we're currently getting, like the total index to what we currently are, like what pile we'll be getting. So it'll be the length of the piles minus 2, right? That's going to give us the index of the second highest pile. And then I'm going to store n as like the number of piles we're going to be able to get, which is 1/3 of the length, right? So for example, in this one, we have 6 piles and we get to get 2 of them. And then I'll just have a total variable, which will accumulate how much we're getting. And I'll do a loop just to count up. So we'll get the value of all of the piles at end, which will initially be the second highest, but then we need to move that down to, right? We're like skipping over every other pile, and then we just return that total. And okay, we need to log in. Just trust me that I guess if does anyone care about seeing it run? Because I copied this. This is correct. Okay, yeah. So that's that problem. That's one greedy problem. And if we have time at the end, maybe I could go over some other ones, but we'll go back to the slideshow now. So that's the example of how you'd write one sorting is a common operation you have to do. So we didn't really have to make specific choices there. Like once we've sorted it, we kind of know where we are. We don't have to like look at options, but it still qualifies as a greedy problem. Is there any way to make it more efficient? So the sorting, so not that I've seen, this is so when sorting this, like dot sort, just the built-in sort is gonna be like n log n. Are you guys familiar with big O notation? Yeah. So that basically means like if the length of the piles is n, uh the sorting grows with n times log of n, because like that's how fast built-in sorting algorithms generally go. Like that's the fastest you can get for sorting. And then this loop just runs, or sorry, that's a little confusing because I've defined n to be another variable. I'll say x. X is the length of the piles. So x log x, I guess. And then this loop runs in, it'll do x over 3 iterations. So that's O of x as well, I guess. This is generally this is pretty fast. The log factor of the piles sorting is pretty insignificant. I don't think there's any faster way to do it. And really the like micro optimizations, if you're talking about optimizing, generally I think of like big O notation, like the overall runtime complexity or the memory complexity. And I don't know of any faster way to do that. You could, make micro optimizations that would make it like technically like milliseconds faster, but really I don't think that's as important as overall like the overall algorithmic complexity, which is like the big O notation. So the next topic we're going to talk about is graphs. Are you guys familiar at all with graphs? You know what a graph is? Yeah? Okay, I'm just trying to gauge a little or no? Okay. Well, we'll talk about it. So, or just define it briefly. So a graph is basically just a set of vertices, also called nodes, connected by edges. Or if you want to define it just more loosely, I can stand up again. It's just really just a network, and we'll show some examples. So there's some variations on graphs, like there's different types of graphs. So one is graphs can be undirected or directed, which means its edges. In an undirected graph, the edges are like bidirectional, which means like basically there's no direction to them. You can go either way, right? From this node, we could go to this node or the opposite direction. In directed graphs, the edges have a certain direction. So for example, this edge is pointing only left. You can't go backwards. In weighted versus unweighted graphs, the edges have some number associated with them. And typically, in most cases, the weight is seen as like a cost of traveling through that edge, but that's not necessarily what the weight means. It could also be, it could be a good thing. Like for example, you could say, like there's some value, like you get paid this amount if you go over this edge, like if you go over a particular road. So the weight really just it could be any number. It doesn't necessarily have to describe like a cost. And now we're going to talk about recognizing when a graph problem is a graph problem. So obviously, if they tell you it's a graph, like if they say these are the vertices and these are the edges, then you know it's a graph problem. But it's not always given that way, because problems could be phrased as what's called an implicit graph, which means they don't tell you it's vertices and edges. Really, it's just they give you this problem statement that involves some states and some ways to transition between those states, or some connections between those states as well. So one classic example is like social networks. So if you have a bunch of people that are connected like on social networks, you can model the people as the nodes and the edges between them as connections, like if they're following each other. And depending on the social network, it might be, directional, like directed edges. Like on Instagram, you could follow someone and they might not follow you back. So that's directed edges. Whereas on like LinkedIn, when you're connected to someone, it's a bi-directional thing. So that would be undirected edges. This graph is a little complicated, so don't look too much at the individual states. But the idea is just Rubik's cubes. You could model like the state of a Rubik's cube, and it's adjacent. So one term is nodes are adjacent if they have an edge between them. And so these states, for example, yeah, I don't want to get too much into the colors, but like if you can go from one orientation of the Rubik's cube to another in just like a single turn, then they're adjacent to each other. So you can model like how you could move from one orientation to another by moving between the nodes that are adjacent to each other. So that's like doing a turn this way, doing a turn this way, and so on. And one really common way, I would say the most common type of implicit graph that I know of is like a grid, a 2D grid maze. there's a lot of problems where they'll give you like, a start and an end, and it's just on a grid. So they might be given to you as just an array, like a 2D array. And really, it's not explicitly given to you as vertices and edges, but the idea is from any of these like empty spaces, these white spaces, you can travel to an adjacent white space. So if a white space is next to a white space, you can travel like to the adjacent ones. And the black walls are like separating those vertices from being connected. And you can apply algorithms on these graphs to like solve problems. So for example, one common problem that we're going to talk about is called the unweighted shortest path. So if I go back, unweighted shortest path is just finding. So unweighted means an unweighted graph. So the edges don't have weights, which just means it's the shortest path in terms of the number of edges. So in terms of this grid maze, it would be like the shortest path in terms of number of moves, right? So like if I move one space down, that counts as one move. So that's a common type of problem. And if we're just trying to find the shortest path between two connected nodes, we can run a BFS, which actually, give me 1 second. Okay, never mind. I have a little visualization of BFS, which a BFS stands for breadth first search, which means basically you're expanding outward from a node, like gradually, instead of just going in one direction, like really fast. And so the property of that property of a BFS, that means you're expanding out like gradually, like layer by layer, means that once you reach a node, like if you have a specific start and a specific end you're trying to reach, when you reach that end node, you know that you found the shortest path, because if there was a shorter path, you would have found it in an earlier layer. And I'll show you just a little visualization. So if I make a grid like this, and so these are like the start, and this is like the end, and a BFS will expand outward gradually. So it'll like, make a larger and larger, that gray area is what it's visited, and it'll find that path. Whereas a DFS, or depth first search, it means it goes in one direction, like really long, and it just kind of chooses those kind of arbitrarily, like what direction to go in. So for example, it'll start going left, and then it'll just sort of snake around like down. And so that means the path it finds is way longer than is necessary, because it just happened to choose like the wrong direction initially. So to find an unweighted shortest path, you run the BFS. Weighted shortest path is a little more complicated. So now we have the same or similar goal. We're trying to find a shortest path, but the problem is we're defining that shortest path differently. So now the edges actually have weights. And we're trying to find the path that minimizes the sum of the edge weights, right? Which is different than the number of edges. For example, in this graph, if 1 is our start and 9 is our end, if we just did a BFS, which would be incorrect, we would find the path 2, 1, 7, right? Which is only 3 edges, which is good. It's few edges, but the fact that the 7 is like weighted so highly means that it's a farther path in terms of the sum of the edge weights. So this path, which is shown with the red arrows, the 2, 1, 1, 1, 1, even though it's technically more like number of edges, the sum is lower. So we need an algorithm that will find us that. So that is Dijkstra's algorithm, or that's one way to do it. But honestly, Dijkstra's is a little complicated, and there's a few slides showing the animation. So I think I'm gonna skip that and come back to it if we have time, because I want to talk about dynamic programming. And this is kind of a more difficult algorithm. It's probably not super likely to come up. So we're gonna skip it and come back to it. So this is a good problem though, number of islands. So this is a similar implicit graph type, which is like the grid maze. It's similar to that, where we get this 2D grid, and it's just zeros and ones. And 1 is land and 0 is water. And we're trying to answer the question, how many islands are there? Right, which means if we can only move horizontally, that means like this group of ones that are next to each other, because it's adjacent land, it counts as the same land. So this one are all the same island. And then this one is diagonal, so it's on its own. these 3 ones are grouped together, so that's an island. These 2 ones are on their own, that's an island, and so forth. And to do this, we can just iterate through the nodes, like go one, like just do a for loop over them. But at each node, we need to maintain like an array or be able to mark the nodes as visited, like whether we've seen these nodes before. And then when we reach a particular node and we see that it is land and that it hasn't been visited before, we do either a BFS or a DFS. And in a lot of problems, you can do either in order to find all the nodes that are reachable from that node. So for example, I'll draw again. If we're looping over all these nodes, when we get to this one, we see that we haven't visited before. So we say, okay, we're going to start a BFS or DFS, either one you want to do. Let's say we're doing a BFS. So that means we expand outwards and we say, are there any ones around me? And they say, and yeah, there are. So you can move to this one and mark it visited as well. And then again, you just keep searching. So are there any ones around this one that we're currently on? And yeah, there are. There's this one. So we mark, so, and then there's no more ones that are adjacent in terms of horizontal or vertical. This diagonal, we're not allowed to travel diagonally. So now we've marked all those nodes as visited, and we increment like a counter when we first visit the first one. So that means we found one island and we've explored the entire island. And then we continue like the for loop, the iteration. And so when we reach a second node, we see it is land, but it's already been visited. So we don't visit it again. So we just continue. When we reach water, we don't do anything. So we just skip over the water. We reach the one again, it's already been visited. And we continue. 0 has already been visited. And then when we reach this one again, since it's unvisited, we visit it and we start the BFS or DFS again. So we expand, we say, is there one around me? You mark it and so forth. So you're exploring the entire island and saying that we've already visited all these nodes in this island, so you never visit it again. And there's a formal term for this in graph theory. It's actually called a connected component, which means like all the vertices, everything is reachable from a single vertex or a single vertex. So an island in this context is a connected component. Well, and so we continue iterating when we do a similar process. We mark this one as visited, increment a counter, and so forth. And we're going to actually do a LeetCode. The next LeetCode we're going to do is very similar to this. And by the end, basically the number of times we reach an unvisited node and we increment that counter is holding the number of islands, right? Because that's the number of islands we encountered. Oh, this is trash can. Yeah, perfect. Okay. Yeah, so we're going to do this one. So it's not number of islands, but called number of provinces. So it's a similar problem, but it's going to be a little simpler. So I don't have to write so much code because we don't want to take forever. Instead of being given to you in terms of the grid, the implicit graph, it's in terms of an actual explicit graph, which makes things a little easier. So you can read it again, but it's a similar problem. So we have the cities and cities, and some of them are connected to each other, some aren't. So if city A is connected to city B, and city B is connected to city C, then A is indirectly connected to C, which basically that would be like an island. It's all the connected cities. So for example, in this, so for extra visualization, 1 and 2 are connected, so that altogether is like the connected component, or in terms of the islands, that would be like an island. And 3 is its own island. And then here, 1, 2, and 3 are all their own separate islands. Right, that makes sense. Is it big enough again? It's like the same size as before, yeah, okay. Okay, so let's get started coding. So similar to what we did before, we're gonna have to iterate over all the cities and explore everything. If it's unvisited, explore everything. And we're gonna need a visited array to make sure to keep track of whether we've already visited a city or not. And one thing to mention is that unlike the grid before, this is like an explicit graph, and this is given to us in a form called an adjacency matrix. So that means it's like a matrix of ones and zeros. So a matrix is just like the 2D grid. So in this case, if we have like So copying down this one, 1, 1, 0. Uh, 1, 1, 0, 1, 1, 0 again, and 0, 0, 1. This means the row and column gives you like what vertices are connected, as in if I'm gonna like label the rows. So this one here means is like basically a Boolean saying that or this one actually, this is a better example. That means 0, right? The column is connected to 1, like node 0 is connected to node 1. Actually here they're labeled as like 1 index, like 1, 2, 3, but so that means really that 1 is connected to 2. And then this 0, for example, means that 2, or in their graph, 3 is not connected to 2, right? There's no connection. And the ones along the diagonal are just that a node is connected to itself, I guess, which sometimes they don't use that formatting. But anyways, let's get into the code. So we're going to have a separate function for a DFS, but for now I'll just define like how we need to set things up. So I'm just to define this variable n to store like the number of vertices. And then I'm going to need a visit array, which initially everything's unvisited. So I'm going to say, this is a list comprehension if you haven't seen it. This is just making a list of length n that's all filled with falses. And then I'm going to need a count variable. Like I said before, we need to count the number of times we visit like a new component. And then we're going to need to loop over all our vertices. Right, so for I in range n. And if we haven't already visited it, if I is unvisited, then we need to visit it. And that counts as a new component. So we'll say count plus equals 1. That's a new component we found. And then we'll call this function that we haven't defined yet DFS, where we need to give it like what vertex it's trying to start exploring from. We need the adjacency matrix so that it knows, what it can explore, what's already been visited, and is a little helper, like a helper variable, to make things convenient. So we don't have to take like the length of is connected again. And then we're going to return the count. The number of times this is incremented means the number of times we find like a new component that we have to explore. And then up here, above the class, actually, I'm going to define our DFS function. So the DFS function is what's necessary to ensure that when we reach a node that's been unvisited, that we explore everything it's connected to. So for example, when this code runs, we'll iterate over the nodes, we'll find one, and it'll explore everything it's connected to. So that's what's necessary to mark 1 is visited and 2 is visited. And if it was connected to anything else, mark all of those as visited as well. So I'm gonna have a parameter called current, which is basically like the vertex that we're currently at. And I'm defining that as an int as well. That type int isn't really necessary. I'm going to delete that. We have the adjacency matrix, which they call is connected, but I'm going to call it adjacency matrix here, or adjacency mat. The visited array, like what's already been visited, and then n as well. And what we need to do in our DFS is mark where we currently are as visited, right? So we're visiting our current node. And then we need to loop through all the adjacent nodes, which means like find all the nodes that are next to this current node and DFS from them as well. So DFS, you can do it with a stack, or you can do it recursively. We're going to do it recursively just because it's a simple way to write it. It's very fast to write. So that means like we'll be calling the DFS function from inside DFS. So we need to loop over everything in the adjacency matrix, or really this is n, but I guess I'll leave it as length. And we say if the adjacency matrix, so there needs to be an edge there. We need to check to make sure that there's an edge there. So if the adjacency matrix at I, remember that like the rows and columns represent like the two nodes that we're trying to check if they're adjacent or not. So if it's equal to 1, that means they're adjacent. So we need to check that. And if we haven't already visited I, then we can DFS from there as well. So we'll DFS I, and we need to give it the adjacency matrix, what's already been visited, and n as well. And that's it. That's the code. I have to log in. I'll log in, I guess. Or it might, okay, this better not like send me like two-factor stuff. Yeah, we didn't run the first one, Max, because it would have made me log in. Okay, good. Obviously. Oh, whoops.
You're so confident. You're just like submit.
Don't waste time. Okay, there we go. Thanks. So that's pretty fast. Sometimes the runtime complexity, honestly, on LeetCode is pretty inaccurate. Like if you submit it again, it'll change a lot, but that's fine. So like I usually don't pay too much attention to like the runtime as long as the time complexity isn't too bad. Where'd my tabs go?
What?
My tabs at the top. Google Slides. This keyboard.
What?
F11 or something?
Yeah, yeah.
Okay. I'm not used to Windows, guys. Sorry. Okay, and now we're going to talk about DP, which is a pretty big topic, dynamic programming. And I called it kind of jokingly brute force but smart because it kind of is a little bit brute force, like it explores the whole solution space, but it kind of does a little bit of smart techniques. Oh, right, stand up again. So that it's not as slow, nearly as slow as brute force. So to recognize, to be a problem that's solvable with DP, that DP will work well on, we have these two properties, these requirements, and they're these weird names. It's called optimal substructure and overlapping subproblems. That's a little bit like opaque. Like, what does that mean? So optimal substructure basically means you can find a solution to the overall problem that you're trying to solve by solving basically the same problem, but with some smaller or simpler input. So we call that like a subproblem. And that means when we solve that smaller subproblem, we'll solve that in terms of even smaller problems. And so we'll eventually reach just like a case, like a very simple case that we can solve, that we know the solution to. That's called a base case. And then overlapping subproblems, that means that we'll end up solving the same subproblem. So like the same function with the same inputs, same parameters, multiple times. So that means if we just do it again, we'd be like repeating the work. So we need a technique that kind of saves the work from that subproblem call. And so that when we call it again, we have like that value memorized. We already have the result memorized. And we'll go into that. So this is what I was saying. When we use a list, and sometimes it needs to be multidimensional, like an array of arrays, to store the results of those subproblems, so that if we ever need them again, we already have it stored, and we don't need to repeat the work. We can just get it from there. And like I said, the base case is just a simple case with a defined answer that we can just immediately return. And then what's called a recurrence relation tells us how we get from a subproblem to a smaller subproblems, how they relate to each other. So I know this is a lot at once, but we'll get into it. So in general, this is like if there's two ways to do DP, and this is one of them. We'll go into like the two types. So if you do it what's called top down, which is recursively, this is a general pattern for your function for your like that you're solving. So DP is like the list, like the table of subproblem results that you have. This comment means like I haven't filled it in. So there you would put a base case here, but we don't have a base case because we're not talking about a particular problem. And then this is what's called the memoization, which means if DP at A, which for A is just like whatever input you have, whatever state you're at, if it's not -1, which generally we use -1 to say like as a placeholder value, because typically -1 is a nonsensical value, so we won't ever actually get it from a subproblem. So if it's not -1, that means we've already found it because we'll fill it in when we find it. Then we've already found that we've already done the work to find that answer to that subproblem, so we'll just return it immediately. Otherwise, this is like the first time we're doing the subproblem, so we haven't stored it, we haven't memoized it, so we need to do like the recurrence relation. So the answer is going to be that like recurrence relation. That's going to give us that result, and that's like the actual work. Yeah, go ahead.
Hear about this stuff overlapping substructure.
Yeah.
At the end of the day, like, this is just like
Mm-hmm.
you have your base case,
Mm-hmm.
and you have like your going into like calling the recursive function again. The only difference is you're storing the answer that you're returning, and if you've ever like found that answer before, you just return the answer instead of doing all of it. So it's really just You can look at it just like a recursive function.
Exactly.
You're storing what you've already.
Yeah, exactly. Yeah, this part and then this part at the bottom, like Max was saying, is you store it for future calls. So if you ever call solve again for the same A, we have it stored here, dp at A equals answer. And so we'll be able to return it if we ever need it again. So we'll get into this. So as I've mentioned before, there's two types of DP. So, or there's two ways to solve DP. So the last one we saw is recursion. It's called top down, which just means you're doing some recursion, which means you're calling a function within the same function. And then you're what's called memoizing that, which is the memoization is the DP table. Like we're storing the results of those past calls. And then bottom up means that there's no recursion. You just iterate like over a table and you're doing it in such a way that you do it in a particular order so that you don't need any recursion because basically the results of those smaller, you do the results of the smaller subproblems first so that when you get to the larger subproblem, you've already calculated the results for the smaller subproblems. So you can just look back in the table and it's already there. I'll explain a little bit more about what that means. So one very simple classic example for what DP can do is the Fibonacci sequence. So I'm sure I would think we're all familiar with Fibonacci, but in case not, it's just every number is the sum of the two preceding ones. So for example, like 8 is the sum of 3 and 5. And you just start from 0 and 1 and build up. So in our case, we know that the first two elements will be fib at 0 will be 1 and fib at 1 will be 1. Right? So those are the first two elements and that will be our base case. And then the recurrence relation basically saying like how the elements of the list or how the subproblems relate to each other is that fib at I is just the sum of fib at I minus 1, so the one before it, and then fib at I plus fib at I minus 2, so like the previous one. So to fill in the function, right, this like filling in the template that we had before, solve is now going to be like I, what index of the list we're solving for. So these two are the two base cases. If I is 0, we can return 0. If I is 1, we can return 1. This is like the memoization. If we've already found the result before, just return that result. And then this is the recurrence relation. So answer equals solve. So we need to recursively call the function with a smaller version, I minus 1 and I minus 2. And this DP table is just storing everything. And then we store the result for future memoization and return it. And so this is the recursive. Oh, you can't see that well. Can I remove this? Okay. So if you were just doing recursion without memoization, this is what the tree would look like, right? When you call fib5, so this is if you didn't have the memoization, if you didn't have that DP table, it would call fib4 and fib3, and they would both branch off into like these big trees. So like fib4 would call fib3, which would call fib2, and then you hit the base cases. But you can see here, like for example, this fib3 is being called in 2 places, which means fib2 is actually being called in 3 places, right? So there's a lot of repeated work being done. And if we did a higher number, like this gets even worse for higher numbers. Like if we did fib6, then it would be even worse because we'd have this fib5 tree and like the fib4 would be like copied and it would be like the child of fib6 as well. Basically, this large tree means it's bad. It's like repeating a lot of work. We're calling the same function many times. So that would be what like normal recursion is. But with the memoization, it means that if we're just doing like down the tree at first, when we do fib5, it calls fib4, calls 3, calls 2, calls 1, gets to the base case. Once we've calculated this 2, then when fib4 needs fib2 later, this rectangle around it means like we're hitting that memoization case. We're seeing that we've already calculated the result to fib2, and so we already have it. And so we can just cut it off right there. And that makes things literally exponentially faster. If you just did it with recursion, you would have exponential runtime, right? It's like the golden ratio, like 1.6 something to the power of n. It's just really slow. And it would get really, really like, it gets exponentially slower as you want to calculate like higher Fibonacci numbers. With memoization, it's linear. So like what's O of n. So if you want to calculate fib at 100 versus fib at 200, it's only like twice as slow as opposed to like way, way slower, like prohibitively slow with just basic recursion. So moving on to another problem, a little more advanced problem that we can solve with DP. So if we have a set of coins C, we want to make a certain amount of change, K, in the fewest number of coins. We want to use few coins if we can. So you might initially think that we can just greedily take the largest coin that we like that can fit, which works for some sets, but it doesn't work for all. And here's a counterexample. If we have the coins like 1, 5, and 8, and we're trying to make 10 cents, if we just greedily took like the largest that we could, we would take 8, and then we couldn't take, and then we'd have to take 2 1s, right? Because we couldn't fit another 5 or 8. And that would give us 3 coins. The actual optimal solution we can easily see is just take 2 5s, and that only requires 2 coins. So that's better. So how do we do it if we can't do it greedily? Well, we're talking about DP, so obviously DP. So our DP table is going to store basically the result, which is in general the pattern. DP is going to the table that stores like your memoization, which is by convention, I guess, called DP. At a certain index, it just stores the result of that subproblem at that, like for that index. So basically, DP at K stores the minimum number of coins required or needed to make that number of cents. So generally that means you're going to make the table as large as the like overall problem that you're trying to solve. So for example, let's put this into specific examples, and I'll talk about these 2 bullet points in a second. If we're solving, like, if we want to solve for 10, like for K equals 10, like we were doing here before, we only need to make the table as large as 10, technically 11, right? Because we want to be able to index 0 through 10. But anyways, so each of these indices, so K is the index, and DP at K is going to store the result, like some value, which means is the minimum number of coins needed to make that K. So for example here, to make 1 coin, we need to just take the 1 cent coin. To make 2 cents, we need to just take 2 of the 1 cents, and so forth for 3 and 4. But then when we get to 5, we can just do it in like 1 cent. Because we can just take the single 5 cent coin. So to actually calculate this, the recurrence relation, if you think about like how these numbers relate to each other, the best way to make K sense is to basically look back in the list. So you need to take 1 extra coin, obviously, but then you're going to try and you're trying to minimize the number of coins. So that's what this min means, the minimum, like minimizing. We're looking back at DP at K minus C at I, which means like the values of the coins in your set C, which, to put it in more specific terms, like if we let's talk about the example. So the 1 plus is just because you're taking like an extra coin from that past value. But basically, remember, we have 1 cent, 5 cent, and 8 cent coins. And we're going to be looking back in our table 1, 5, and 8. So for example, if we wanted to make 10 coins, and we've already calculated this table like with using this DP technique, and we're just filling in like the last value, and I'm showing you how it's done. We could do it from 9, right? We could go from 9 to 10 and take by taking a 1 cent coin, right? So if it requires us 2 coins to get from 9 to 9, then it would require us 3 coins to get from 9 to 10, right? If we're going through 9, if we make 9 and then we take a 1 cent coin to make 10, that would require 3. However, if we had a 5 cent coin, or if we made 5 cents the optimal way, which requires only 1 coin, then to get from 5 to 10, we can take a 5 cent coin to take 1 extra coin. So that would only require us 2 coins. And then our other choices, we could also go from 2 to 10 by taking an 8 cent coin, right? But it requires us 2 coins to get to 2. So to go from 2 to 10 and taking that 1 extra 8 cent coin, it would give us 3 overall. So the best option, basically, you're trying to look at the minimum of these. So 2, 1, and 2. The smallest one here is 1. So we want that one. So that's why the green arrow is saying take the 1 and add 1 to it. And that means it costs 2 coins. It requires us 2 coins to get to 10, because we can go through 5. We can make 5 and then take another 5 cent coin to get to 10. You're gonna say something?
No, can I take a ring?
Yeah. We're fine.
Okay, so we're running low on time, so I think we should skip this one.
Yeah. This is probably complicated.
Yeah, this is probably the hardest problem on here. So this is dynamic programming, but it's in 2 dimensions. And so what that basically means is the question is you talked about fractional knapsack before, right? Basically, you get a bunch of items with weights and values, but you can't take parts of the item. You have to take the item as a whole. So you have to say like, okay, what set of items will give me the greatest value overall when I have like a set max weight. And so what you have to end up doing is construct a table where you memorize based on like the index of the item you're currently like saying like, oh, do I want to take this? And like your weight left to take. So what that like ends up looking, again, I want to go quickly through this. I kind of want to skip it. Is like, this is the recursive call on like, say I'm trying to get through all the items. So I'm on the bottom right with like 6 spots left in like my knapsack. All the zeros are base cases because they're like, they mean you've either taken all the items or you have no space left in your sack, so you can't take anything. And so you have to like, you should like, if you're interested, look over this. The pink arrows are essentially saying like, take this item. So you're going to be adding its value. And the blue is like, skip this item. So you're just going to be looking at the value above. And you are going to be like maximizing. And then, so I do want to go over this one. This one's more similar to the one Kai went over. And this is longest increasing subsequence. So basically, given an array of numbers, we want to find the longest increasing subsequence, which is just a set of numbers in an order that don't have to be consecutive, that are just increasing. So for example, in here, like 6 and 6, 9 is a subsequent increasing subsequence. And if we want in the largest one is obviously just the longest one. So 2, 3, 5, 7 or 2, 4, 7 would be the longest one here. And in order to find that, obviously you start, you're trying to find the longest increasing subsequence that ends with each of these elements. So like 6, obviously the longest one that ends with 6 can just be 6, so 6. Here 9 is greater than 6, so the longest one that will end with 9 will be 6, 9. So you look at 6, oh, that's length 1, add 1 to it. 9 stores at 2. 8, it can't be added to 9's subsequence, but it can be added to 6, to the subsequence that ends with 6. So you say, okay, the longest subsequence that ends in 6 is at length 1. You add the 8, it becomes length 2. 2, again, it's less than everything else that came before it, so it can't be attached to a subsequence. 3 can be attached to 2 subsequence. 5 can be attached to either 3 subsequence, or the subsequence ending in 3, or the subsequence ending in 2. The subsequence ending in 3 is longer. And we're trying to find the longest increasing subsequence. So we take the one that ends that has 2 elements in it, the 2 and the 3, and then we add the 5, making it 3 elements long. Again, 1 is less than everything that came before it, so it can't be added to a subsequence. 4 can be added to 2 and 3. You add it to the 3 to maximize, and 7 can be added to the subsequence ending in 4, 5, 1, 2, 3, whatever, like all the numbers below it. And what you end up doing is you say, okay, the 5 and the 4 are the longest because they're both 2, 3, 5 and 2, 3, 4 respectively. And so you add the 7 to the subsequence of those. And that's the length 4. So that's your longest increasing subsequence, is the subsequence ending in 7. Now it is worth noting, this isn't always your answer. So your answer isn't always going to be in this last box, because if I had like a 0 there, that would be just P1. So you have, in order to find the answer, you have to look over every single box in the DP table and find which is the largest, because the DP table is just storing the largest increasing subsequence that ends with the number at each index.
Do you want to do the code then?
I don't think we have time.
Okay. So I was gonna do, you want to talk about it? Okay. This is an example problem if you want to do it on your own, but we don't have time to solve it. It's a pretty simple case of DP, but you need to know a little bit about the binary properties of like binary numbers. So that's everything. That's it. Oh yeah, we have a lot of pizza. So get seconds, please. Oh yeah. Yeah. If you came a little late and you, please sign in.